we're going to cover. So we'll run a little bit ahead of the lecture. Okay. Our lecture is way behind the schedule, anyway, so that makes my section a little bit hard to organize. So this time I'm going to cover just chapter 7 and 8 all together. Chapter 8 is a pretty small chapter, especially in this class. We will not cover the second approximation method. Well, last year we also covered perturbation theory, but here not, so it makes this one easier. So we'll continue to finish chapter 7 today, and then cover chapter 8, and that's all. Okay? So the first thing about chapter 7, after the wave functions we talked about last time, is the quantum numbers. Okay, this concept. So quantum numbers, as I mentioned last time, are used to describe a certain quantum state, and to be more accurate, it should be the electronic state. Okay. Contains at least, for this chapter, we learned 7 quantum numbers here, and we've already talked about the first 3, with n as the principal quantum number, L as the obviously angular momentum quantum number, ML is the magnetic quantum number. Okay. So today we're going to cover those 4. And can you give me the name for S? Spin what? Spin quantum number. Okay, spin angular momentum quantum number. So that's why we kind of distinguish this one with putting something in there. So they are both angular momentum quantum numbers, but for L is orbital, for S is the spin part. Okay. And how about MS? Magnetic spin quantum number. Okay. So it's pretty easy to remember, to memorize it. You place M, that means magnetic. That's just M. M stands for magnetic. S is spin quantum number. So you just need to put a magnetic in front of the name here. In front of the name here, and that's magnetic spin quantum number. Okay. L to J. Total angular momentum quantum number, and MJ. Use the same trick. Magnetic, the same. Okay, magnetic total angular momentum. So those are just names, okay, for you to communicate. So how can we communicate with each other? By calling their names. Okay. And they have their own possible values, right? And let's make a review here for the first 3 we talked last time. So the possible value for n is for R what? The possible values for n. 1, 2, 3. First, it must be integers, and it must be positive integers, so not including 0. And how about L? 0. 0. The next one is 1 until n minus 1. So determined by n. How about MS? FL.
Integers including 0 and then plus or minus 1.
So let's say 0, first one 0, and next one is positive minus 1, plus minus 1, plus minus 2, until plus minus L. So it's actually a symmetric distribution, right? You put the 0 in the middle. So 1 is negative 1, positive 1, negative 2, positive 2, until negative L, positive L. Then how about S? Let's say for hydrogen atom. In this chapter, only talking about hydrogen atom. So what's the possible value for S? 1/2, always. Okay? But for other atoms, may or may not be 1/2. Okay, we will learn how to determine S in chapter 9. And then how about MS? Plus minus 1/2 for hydrogen atom. And for general, it is from negative S to S with an interval of 1. So that means if S is 1/2, simply means from negative S to positive S with interval of 1. This is already, the interval is already 1, so just this 2. But if we have, let's see, 3/2, could be possible for many electron atoms. Then the possible MS value is from negative 3/2 to positive 3/2 with an interval of 1. So this one plus 1 equals negative 1/2. Plus 1, positive 1/2. Plus 1 is positive 3/2. So those are four. The four S values, S shortcut. NS values for S equals 3.5. Okay. Then how about J? Let's see the better one. Is it shift from what to what? It's a scope. And think about J. J related to L and S. The total angular momentum is a vector, addition of the orbital angular momentum with spin angular momentum. So it must be related to the two quantum numbers.
L1 is S.
L what?
L1S.
L S, that's the upper bound. Now still have a lower bound.
So 1/2 is lower bound.
1/2.
Yeah. Because it has.
But 1/2 for acting,
Can be lower than 1/2, right?
can be lower than 1/2. Yeah. But usually, we choose absolute values, which should always be a positive value. So let's see, with an interval of 1 as well. So the thing, the trick is, let's say S equals, for everything atom, okay? 1/2, always. L equals, let's say, 2. So my first question is, what's the orbital here? Is the S orbital, P orbital, D orbital, or what? S, P, D, 0, 1, 2, so it's D orbital, right? Okay. So the possible value for J is, starting from L minus S, but you always with the positive value, so 2 minus 1/2 is 3.5, right? The next one is 2 plus 1/2 would be 5.5. And then with an interval of 1, so it's just 3.5, 5.5. So just two values. Okay? And if I change, I'm going to change the S value. In chapter 9, we'll change the S value. There will be more J values, but they all follow this one. Okay? You can try. Okay? Just ask you to try and maybe after the section. If S is 3/2, L is 2, how many J values you can get, and why are they? Okay? That's for J, and how about for MJ? So MJ is the same as MS. So from negative J to J with an interval of 1. And the same trick applies. So you just change S value to J value, and you can. Okay. Any questions about this? It's pretty important, especially the J values, because you need it to write down the term symbol. Okay. All right, so let's go into 7 individual quantum numbers and have a somewhat detailed discussion about their physical meaning. The first one is principal quantum number, usually with a small letter n. So it determines the total energies of the energy level, the state of the orbitals. So the equation used is here. So it's actually the same equation we derived in Bohr model. Okay, this one is consistent with the Bohr model. With a rather constant, but with the negative side over n squared. And it actually also determines the average radius for each orbital. So how? So actually you will see here, based on this figure, you will get but we know within for the Bohr model, we only have one s orbital and we have two s orbital, and they have different radius, with respect to the distance between the s orbital and the nucleus here. So the same thing here. Although we know for quantum pictures we do not have the pretty sharp orbitals there, but we can use this one to actually evaluate or to actually qualitatively compare the average radius of that orbital. Okay. Can we still remember this figure? So for this part, it's actually the same as Bohr model. So this is what the energy level we used in Bohr model, and this is exactly follows the equation for hydrogen atom here. For each different energies, this is the ground state. First excited state, second excited state, they have different energies. And the energies are largely depends on quantum mechanics. Well, I did not say it only depends on n, but I mean they largely depend on n because of this equation. Okay, so those energies are largely dependent on n. So that principal quantum number mostly determines the total energies of the orbitals you have. Okay, so that's the principal quantum number. So those En is the same thing here. Okay. Next one is the quantum number L, and orbital angular momentum quantum number. So it determines the magnitude of orbital angular momentum of the orbital of the electrons in that orbital. Okay, can be evaluated by this equation. So the L, the magnitude of the orbital angular momentum equals quantum number L times square root L plus 1 and times h bar. And pay attention, h bar is not in the square root. Okay, so it's simply with the unit of h bar here. So it determines the orbital shape. Like we have lots of hydrogen atoms with the wave functions or the probability density distribution curves we talked about in last section. So they are all determined by actually the L values. Okay, you have s orbital is spherically symmetric. But if you have p orbitals and d orbitals, like this one is, anyway, it's p orbitals. Those things, d orbitals, they change the shape. Okay, so let's do the orbital quantum number. Any questions? Okay, next one, the magnetic quantum number, ML. This one determines the magnitude of the z component of the angular momentum we talked about in the previous slide. Again, the equation is this one. So the left-hand side is the z component, the magnitude of the z component of angular momentum equals just the quantum number times h bar. Okay, and the physical picture is something we talked about actually last time. So we know we have the L values. The L values is also quantized because it's determined by the quantized quantum numbers. So it can only be some values among the within the whole space. And let's say if we choose this one, and the length for the cone here, the psi length, represents the magnitude of the orbital quantum, the orbital angular momentum. So it's like this, and with the direction here. And if we project the orbital angular momentum to z-axis, we'll get another vector. And the magnitude of this vector is defined as the magnitude of the z component of the orbital angular momentum. Okay, so this length is determined by ML. Right? So it determines the orbital rotation. So we saw L determines the shape, and not ML determines the orientation. So for example, those are the 6 of the F orbitals here, and we can see they are all kind of 6 parts, but they with different orientations. This one facing up, this is facing to this axis. This one a little bit different. The packing style, so that the orientation is determined by ML. Okay, it will not change the shape, but change the orientation. Okay, so let's see the magnetic quantum number. Next one, spin quantum number, is a little bit abstract. It determines the magnitude of the spin angular momentum. Okay. Well, the equation is pretty straightforward. It's the same thing as the L1. So this just changes the L to S, and everything is the same. But the hard question is, well, it's pretty hard to understand in the picture. Right? We cannot give you the picture to describe the spin, something like motion for the electrons. But the electron is not like real spinning as you think in your mind. It's not that. It's not something like that. It's just an intrinsic property, like charge and mass for the electrons. So we cannot actually present a pretty accurate picture for you to see, oh, this is actually the spin angular momentum. So it's just something pretty abstract. Okay, and it was discovered by this experiment called the Stern-Gard arch experiment conducted in 1922. In that experiment, they used use the silver atoms generator, generate lots of silver atoms, and pass them through a irregularly distributed magnetic field. And this beam will be split into two. Well, based on the classical predictions, this beam will be split as a line. So everywhere with the equal chance to heat. But the reality is it only heats two ports here, two spots here. So simply means actually the spin angular momentum here, spin angular momentum is quantized. Okay, it's not like people think it's consecutive before, so it's just quantized. So they only have two individual states. Okay, so based on this experiment, they actually somehow they concluded the electron should have spin quantum here, and it should have spin and angular momentum for that. Okay, if you're interested in this, you can easily search wiki and to look for this experiment and see how they derive this concept, the spin concept from this experiment. Okay, so this is just one experimental observation for the quantized spin of the electrons, or even from atoms. Okay. Next one, magnetic spin quantum number. Again, you can compare to the orbital angular momentum quantum number, L and ML. So the same thing, same way to understand S and MS. So it determines the Z of component, the spin quantum angular momentum as SZ equals MS times H bar. Okay. Same picture, right? If you have this is your total, no, sorry, it's not total. This is the spin angular momentum. Then if we project onto the z-axis, the length here is determined by ms. Okay. So based on that, we actually give the name one is spin up, one spin down. So if your projection, if you're like this situation here with ms equals plus 1/2, so that's spin up, we call alpha state. And if your z component is -1 over 2h bar, so we call this one spin down and we name beta state. And for direct notation to write those states, alpha and beta. Okay, that's what you learned in Gen Chem. Okay, they all derive from ms actually. So we have spin eigenfunctions then. If we have the eigenfunctions here, and for example, the operator, the SC operator, operate on the alpha state will give you the eigenvalue 1 over 2h bar times the eigenfunction itself. And same thing for beta function. Okay. And alpha and beta functions, they are orthonormal. So here I use the direct notation, hopefully most of you can understand. That's just the integral. Okay. If you integral the whole alpha state or the same beta state, they give you 1. So of course, first you need to normalize it. Okay. Usually we'll give you the normalized one. And alpha and beta, if you integral the different two eigenfunctions together, you get 0 because they are orthogonal. Okay. So we see actually this is part of the eigenfunction to describe the hydrogen atom. So the two complete wave functions for hydrogen atoms, besides radial parts and angular parts, should have spin part. Okay, we have either spin up or spin down. So those are actually the two complete wave functions. But in most cases, since alpha and beta part, they do not affect the total energy. They do not affect total energy, and they can be, use the separation of variables and get rid of it. So that's why people, in order to, when they discuss hydrogen atoms, they kind of ignore this one. Okay, they don't want to talk about the spin. But if you want to really emphasize the spin state of the electron, you should put the eigenfunctions from the spin part. Okay. So any questions? So I know this. All those equations, actually it's pretty straightforward. You just keep plugging the different quantum numbers and you can get the value. But the hard part is for you to understand and form the picture in your mind. Right? What are those orbital angular momentum and what are those spin quantum orbital, the angular momentum? Well, those things are pretty abstract things. and we cannot use a physical picture to describe it. You just think about that just like a cone, like what I showed in the picture. Okay, but how that related to the electrons, like position or whatever motion there have pretty unclear things there.
So if the spin doesn't have anything to do with actual spinning, does it have to do with the magnetic charge of the electron?
Magnetic charge.
Magnetic property of it.
Yeah, well, it will.
Okay.
Once you apply the magnetic field, we will see the energy actually split.
Okay.
But the splitting is not caused by MS, but caused by another magnetic quantum number like ML and MJ. Those things. Okay. So next one, J, the total angular momentum, even more abstract. It talks about orbital spin coupling. So after we have orbital angular momentum, we have spin angular momentum. They guys put together with the one electrons, they can interact with each other. And J is the quantum number to describe the interaction. So for example, we have L as the orbital angular momentum, and we have S as the spin angular momentum. So simply orbital spin coupling means you add the two together but by vectors. So you will get J in this one. Okay, that's for J. J is total angular momentum. Okay, this is total angular momentum with this direction and this magnitude. This is air angular momentum. This is a spin angular momentum. So this is orbital. Okay, a more fancy picture is like this. There are three cones. The first cone here, the blue one, is represents the orbital angular momentum, whereas the green cone represents the spin angular momentum. And you add them together, you get this cone, that's total angular momentum. Well, still pretty abstract, I know. But for you guys, if you memorize the equation, if you accept this picture or something like that, think about just like a rotate something. Well, it's not rotate even. It's just, this is just represent the magnitude distribution. So it's pretty hard to find a physical picture to show to you there. Okay, anyway, just try to understand that's in a pretty abstract way. That's just something, the intrinsic property for electrons. Okay. So the mathematical expression is this. So spin angular orbital spin couplings present the J. Okay. And also it determines the magnitude of total angular momentum as this one. Again, you just change L, S to J here, and you get the total angular momentum magnitude here. Okay. So again, the equations are pretty straightforward. And also it determines the splitting of energy level. Okay. Without the presence of the magnetic field. So for example, we have not two p's. So here is the term symbol we'll talk about later. It's not two p's, it just means p, orbital. Okay. It actually can be split to two energy levels according to their J values. Okay. And this splitting actually, if you compare, so if I put the initial energy level here, the splitting is pretty small. It's not that quite obvious splitting, but it's a small splitting here according to J value. If this state has two J values, then it's split into two. If it has n J values, then it's split into n. Okay, later you will be able to tell how many J values if I just give you this term symbol. Okay. And then the last one is magnetic total angular momentum quantum number, MJ. So again, it determines the Z component of total angular momentum. So from here, you can actually compare, group the last six into just three groups. The L with ML, S with MS, J with MJ. That's pretty similar pattern here. And also similar equation to determine. And again, this means you have a total angular momentum. You project on the Z axis, and the magnitude on the Z axis is actually the Z component of the total angular momentum. And we don't have any physical picture to show you the total angular momentum. They're just intrinsic properties for the atom. Okay? Any questions? Well, if you have a hard time in understanding the physical meaning of those things, at least please memorize all the equations we have. Okay, perhaps we will give you in the final exam, but I believe in last year's final exam we have one question which we did not give you those equations. Okay. We asked you to write that and use the equation to do the evaluation. So it's somewhat straightforward for you to memorize. Okay. Just for the angular momentum part, no matter it's angular, spin, or total, it's just something like the quantum number times square root of quantum number plus 1 times h bar, right? And for the z component, it's always m something times h bar. So you can fill in this one, you can fill in L, S, or J. For this one, again, L, S, J. Okay? Any questions? All right, so next part, we'll talk about term symbols. So straightforward anyway. So term symbols is used to label the electronic energy states. Okay, so giving electronic energy state definition. It's not talking about vibrational, not talking about rotational, we're talking about electronic. So in order to label each electronic energy states, we divide the term symbol, which is this one. Okay. So the main part here is just a quantum number for the orbital angular momentum L. And 2s plus 1, here S is the spin quantum number. Okay, this is actually a superscript with 2s plus 1. So it's not S. Okay, it's not S, it's actually 2s plus 1. It's talking about the degeneracy actually. But anyway, it's just 2s plus 1. And the J is the total angular momentum quantum number. Okay, for the L, we have different symbols. But same thing as the orbital notation we used. So, but here is not the small letter, it's the capital letter. So capital letter L also equals to 1, 0, 1, 2, 3, and we have the symbol SPPF with all capital letters here. And you may be wondering why we use capital letters, why not use the small letters, especially for those quantum numbers here? Well, if we're talking about hydrogen atom with just one electron, or hydrogen-like atoms with just one electrons, we can reduce those quantum numbers to small letter. And we know the L reduced to the small letter L, J reduced to the small letter J. And S equals what? 1/2. 2 times 1/2 plus 1 equals 2. Okay, now you can just use small letter. But the symbol also still capital letters. Don't change that to the small letters. Okay. So later we'll see. So just keep in mind, this is the term symbol we use. And based on this term symbol, as you can see, we do not have any number here. So based on term symbol, we cannot know the principal quantum number. Okay, principal quantum number is unknown here. We only know the orbital angular momentum quantum number, spin quantum number, and total angular momentum quantum number. Okay, only know the 3. And why we know that? Oh, we already talked about that. The selection rules. Okay, for transition involves 2 electronic energy states. They should follow this 4 requirements. Okay, so the first one, the change in the quantum number L should be plus or minus 1. So simply it must be changed, and it must be changed by 1. Okay, second one, delta S. So the quantum number S should not change. The third one is delta J. So delta J can be 0, can be plus minus 1. Okay, you can change or without changing. But if delta J equals 0, make sure it's not from J0 to J0. Okay, this is not allowed. So from J equals 0 to J equals 0 is not allowed. Others, from J equals 1 to J equals 1 is okay. Okay, or you can change that one. So here I want to emphasize the delta sign here. I graded the quiz last Friday. Some of you just say, let's say the selection rule for rigid rotator is delta J not equal to 0, right? So here we say delta J, but some of you wrote J cannot be 0. So the difference between J and delta J is, if you just say J, that just means one quantum number. Okay, it's just one quantum number. But once you say delta J, it actually talks about two quantum numbers. The final quantum number minus the initial quantum number. So that's related to the transition, because we know the transition involves two energy states. It involves two quantum number. And the selection rule is about whether the transition is allowed or not, so it should describe two quantum numbers here. So that's why we choose, we say delta J is not 0, simply means these two cannot be equal to each other. So if you just say JF cannot be 0, or just say J cannot be 0, it's a number within this meaning. Okay, same thing here. When you talk about transition, always put delta. And the last one, delta MJ, must be 0 or plus minus 1. Okay? So any questions? Let's derive, let's do a practice. Let's take one orbital is 3D orbital. Okay, 3D orbital with a hydrogen atom. So please derive all the term symbols for this energy state, or for this orbital. Well, we can see, in order to derive the term symbol, we need to determine L. And this is hydrogen atom, so 2s plus 1 must be always be 2. Anyway, we don't need to care about that. And then determine J. Right? So based on this, what's the L value? So the term symbol should be, the symbol there should be D, capital letter D, right? And then the S equals what? 1/2. And then how about J? Well, as I mentioned, what's the possible values for J? What are the possible values? From L minus S to L plus 1, from L minus S to L plus S with the interval of 1. So L minus S is 3/2. L plus S is 5/2, and the interval is 1. So there's no more numbers in between them. Right? So the term symbol, we have 2. And, right? Okay, pay attention. The superscript here is not 1/2. Okay, it's 2s plus 1, so it should be 2. That's the term symbol. And for hydrogen atom, if you want to draw, plot them. So we have two inner states. We know they split according to the number of J values. So which one is actually above? Which one is on the bottom? So the smaller J corresponds to the lower energy states, and the larger J corresponds to higher energy states. Okay. This is just for, so I emphasize here, hydrogen atom. For other many electron atoms may or may not follow this pattern. Okay. Then there we need to talk about another thing, that's called the Hunt rule to determine. So here, it's free of that program. We just put the smaller one on the bottom, larger one on the top. Okay. All right. Actually, you can give you more. You can practice by yourself. You get 4f orbital or like 5. D orbital, whatever. So D orbital should actually be the same for the hydrogen atom. Okay. But within this chapter, you are only able to derive term symbol for hydrogen atom. So if you give yourself a lithium atom, you cannot do it right now. But later you will be able to do it. Okay. Any questions? Okay. So the next part is the energies. energies for hydrogen atoms. So we first want to talk about RS coupling. So with that, from there we introduce to the total angular momentum J. Okay. So in the absence of external magnetic field, it will cause the RS coupling will cause the energy swing. So the Schrodinger equation is illustrated as this one. This one is kinetic energy of the electron, right? This is the potential energy, the attraction between the electron with the nucleus, plus additional term. So that term accounts for the LS coupling. Okay, we'll give this form. Well, this is exactly your Schrodinger equation. And somehow by solving it, you cannot solve it exactly. We use a approximation method called the perturbation method. Not required in this one, okay? You will get the energy. Well, the first part is from the black part, you get the energy of Bohr model predicted, or we talk about many, many times. That's your energy, but with the additional term plus perturbation. Okay, so actually it's not exactly this part, but with some modification. But this perturbation, the magnitude, I mean, compared to this part, is way smaller. So you just slightly change the exact energy. Okay. Based on this picture, we can give you the physical picture like this. For example, we have one s orbital and two p orbitals here. Okay. And without the external magnetic field, in the absence of that magnetic field, if we're only considering LS couplings, it will give you the picture like this. The energy level will split according to the J value. Okay. So let's say one s orbital, we can derive the terms of that. So let's do it again. For one s orbital, how can we determine the term symbol I labeled there? For one s, what's the L value? What's the S value? What's the J value? And what's the term symbol? S. And the superscript? 2. Subscript. Okay. And we only have one inner state because we only have one J value. And for P orbital, we have two J values, so that's why we have 2. And with the larger J on the top, smaller J on the bottom. Or exactly the picture we talked about. And here, one more thing is there are actually many degenerate energy levels within this line. Okay, I did not show you the degeneration. So there are actually, for this one, we have 4 degenerate states. This one have 2 degenerate states. We have 2 degenerate states here. Okay. Those degeneracy equals 2J plus 1. Okay, equals 2J plus 1. So just, have you still remember the radio rotator there? Was there a quantum number J there? And the degeneration is 2J plus 1, same thing here. Okay, degeneration. So let's do the, just considering LS coupling, I mean without the external field, but once when we apply the external field, after the presence of the external magnetic field, will cause another energy splitting, which is called Zeeman effect. Okay. For this situation, the Schrodinger equation decides LS coupling. So here, I'm still considering LS coupling. But with 2 more additional terms. Okay, this one accounts for the interaction between the angular momentum, the orbital angular momentum with the external magnetic field. Well, this term accounts for the interaction between your spring angular momentum with the external magnetic field. So you have 2 more energy terms. And again, you have to use perturbation method to solve the energy like this. Okay. Now, this part is what we learned before, predicted by the Bohr model, plus perturbation from LS coupling, plus this graph. This term accounts for the magnetic interaction, okay? Or also accounts for the energy change, based on the external magnetic field. So we have several terms here. So here's the J. It's called the J factor. Depends on L and S. After 1/2 is actually S value. And you have different situations and different J values. And for the beta is the Bohr magnesium, which is also a constant. You can plug in some values into it and evaluate. So MJ, what's MJ? Can you tell me? Magnetic something with a J, the same as a J. Magnetic total angular momentum quantum number. Right, this is a quantum number. And B is the magnetic field strength. Okay, so it actually depends on 4 things this time. The J value, the J factor, the G factor. So 2 situations. Times the Bohr magnesium, which is a constant. Times the quantum number. Times the magnetic field strength.
So when it says along the z direction, does that mean that all of them are going to be along the z direction, or do you have to just calculate the?
So we all apply the magnetic field. We always choose the magnetic field direction and the z-axis.
Okay.
Just for can make your calculation somewhat easier. Okay. So the physical picture is like this. Okay. So first thing is, if we do not consider LS coupling, if we do not consider that, we just apply the magnetic field. Okay, it will split according to the number of ML. Okay, for example, for 1s orbital, we know L equals what? L equals 0. So what's ML, the possible values for ML? Well, that's why we summarize all the possible values before. That's why we need that to derive something here when we talk about term symbol and also energy levels. So we know 1s orbital L equals 0. So ML, the possible value is from 0 plus minus 1 to plus minus L, right? And here L is 0, so it's only 0. That's why ML equals 0. So we split. This energy state will not split. So after you apply external magnetic field, what do we miss here? But things will be different for p orbitals. So we know p orbitals L equals what? P orbitals L equals 1. ML equals 0 plus minus 1. 3 values there. That's why we have 3. And as I showed you before, the energy actually depends on ML. So you have a negative ML, minus 1, then your energy lower. That's the state. And if ML equals 0, the energy will remain unchanged, so that will be this state. And if your ML is plus 1, your energy increases a little bit, will be this one. And again, I want to say, so the energy gap between 1s and 2p, compared to the splitting here, this splitting is very, very tiny. So very tiny compared to the energy gap here. So actually this figure or this energy diagram is not to scale. So I should draw this 2s like way below here somehow, compared to the splitting here. Splitting is just a tiny part. So you can do the evaluation, you will see actually the splitting compared to the true energy, compared to the, it's just this energy gap here is quite small. I think it's 3 magnitude of water smaller, 3-fold smaller than this one. Okay. This is actually the picture when you apply the external magnetic field without considering RS orbital, RS couplings, and which is not quite realistic. The RS always coupled with each other. So the picture, the more realistic picture is like this. Okay, so the first one is we're considering the LS coupling. From the first one, we derive the energy language should be like this. And now I put the terms and the label each one. It's no longer the orbital notation there. Okay. And then we apply the weak external magnetic field. And we will get this picture. So all those energy levels will split according to their nj values. Okay, for example, for S, this term symbol, we know nj, or we know j equals 1/2, right? So what's what are the possible values for nj, or what is the possible value for nj? Plus 1/2 to, better to say negative 1/2 to positive 1/2, right? Because the possible value for mj is from negative j to plus k with an interval of 1. Well, again, here if j equals 1/2, from negative j, negative 1/2, to positive j, which is positive 1/2, with an interval of 1, it just says two numbers. So this energy will stay, this energy state will split into two. And the same for this state. So what's the j value for this energy state? What's the j value?
It's 1/2.
1/2. mj, 2. Okay, positive 1/2, negative 1/2. How about this and this j? 3/2. Positive mj values are negative 3/2, negative 1/2, positive 1/2, negative 3, positive 3/2. So I have 4. So you actually split into 4. Okay. So again, if we do not consider LS coupling, if we do not consider that, that's the previous picture. Once you apply the energy field, once you apply the magnetic field, the energy will split according to their ML value. And once you consider the LS couplings, and you apply the external magnetic field, the energy will split according to their MJ values. Right? And if you only consider about LS coupling, the energy will also split, but this time will be according to their J values. Okay, there are 3 situations there. Okay. And based on this figure, actually, we can derive how many transitions we can have. Those are some questions we can get to. The simple thing is you can just use your selection rule to determine. For example, can we make a transition from this state to S state here? From here to here, can we make the transition? So the selection rule, the first one tells you delta L must be plus minus 1. P to S, that's minus 1. Okay. Next one is delta S must not change. From this S equals what? 2? 1/2. This one? 1/2. Does not change. Good. Next one is delta J can be 0 or plus minus 1. But if delta J equals 0, you cannot go from J to equals 0 to J equals 0. Okay? How about this one? The J is what? So you have this J, 1/2. Delta J is 1. That's okay, right? And delta NJ must change by 1 or remain the same. So this one, 3/2 to 1/2, still 1. That's good. So you can make that transition entry. Okay, but can you make a transition from here to here? Violate which one? Which selection rule? The right cannot be 0. Okay? So essentially the question we can give to you. They'll first ask you to derive this pattern. Once you give the pattern, we ask you something, whether you can make the transition from here to here, or from here to here, whatever, I have lots of choices. Right? But the only thing is you need to know the selection rules. Those 4 requirements. Okay? So let's do one exercise. For transitions involving 2p and 2s orbitals, so here I use the orbital notation. Okay, it's not term symbol, just keep in mind, in order to tell whether the transition is allowed or not, usually we need to convert to terms anyway. But wait a minute, maybe this question does not ask me to use the selection rule, okay? The 2p2s orbitals of a hydrogen atom and tell how many lines should be observed in the emission spectrum. Okay, let's do one by one. I'll give you some time. Let's say case 1. So how many lines should we observe? Let's do easiest situation. Easiest situation. Without considering AS, so no energy splitting. Without the magnetic field, again, energy will not split. How many lines we can have? Have 2p orbital, 2s orbital. How many lines do we have? The transition, emission from 2p to 2s. How many lines?
Yeah.
Just one line, it's one transition. It's one wavelength, right? Okay, case B. Now we apply the external magnetic field, but we still do not consider LS coupling. So in order to tell how many lines, we need to first draft the energy diagram, right? So just apply magnetic field without considering about LS.
So it's just the ML states then? For the 2p?
Let's say how many energy state will this energy state split? Just one line. And y is just split into one. Just will not split. Just y is just one.
We're not considering all this stuff because there's magnetic.
Yeah, if without LS couplings and if just a high magnetic field, energy state will split according to one number.
ML.
ML1. Okay, so 2s. What's the ML? Think about what's ML.
0.
I think L equals 0, so ML equals 0 only. So that's why we only have one stage. Okay. How about 2p? It's also about ML value, right? So ML equals what? Depends on L.
Plus or minus 1.
L equals 1. 0 minus 1, so it would be 3. Right? Then how many lines? Well, there's first one, second one, third one. Can we make transition here? What leads to what?
Delta.
Delta L.
Delta L must be plus or minus 1. So we have three lines. And so for this, and so for this, also another line. And so for this one. Okay, case C. Now we do not apply the magnetic field, but we consider it as coupling. How many lines should we have? I heard 10.
2.
Think about it. 10 is something from your textbook. Well, the initial picture is still there. But now, considering LS coupling, the energy state will split. And the energy will split according to what number?
J.
J number. Okay. For 2s orbital, what's the J value? Well, we need to do some evaluation, right? So the L equals 0. S equals 1/2, all this. I don't need to think about it. I just ask it to 1/2. So J equals, the possible value for J are L minus S to L plus S with an interval of 1. So L minus S is actually -1/2, but we always choose the absolute values will be 1/2. 0 plus 1/2 is also 1/2, so it's just one number. So this will split into, well, will not split. Okay, how about P? Then again, we need to consider what are the J values. Okay, to calculate J, we need to get L first. L equals S equals. So J equals. Right, so we'll split into two unit states. So then how many lines can we observe? First line, second line. Well, how does this one come up? Can we translate there? Well, like what? Again, delta L cannot be 0. Okay, this is within P and P. Okay. So this is P2, 3/2. This is 2P, 1/2. Okay, P2P is not allowed. Okay. Last case, case D. Now we consider two factors together. Once we consider two factors, the inner levels definitely will split, but will split according to one number. A to that. Okay, good. So before we know J equals 1/2, 3/2 for this state. J equals 1/2 for this state, right? And now we need to evaluate MJ. So what's the MJ for 2P then?
-3/2 going up.
Well, that depends on two situations, actually. The first one, if J equals 1/2, we have one set of numbers. And if J equals 3/2, we have another set of numbers. So if J equals 1/2, MJ equals right?
No, it's.
If MJ equals 3/2, so we have actually two sets. So it's labeled as 1 and labeled as 2, so this is 1, this is 2. MJ equals therefore. Okay. And how about the MJ for this one?
Same as case 1.
Same case 1, so it will be how many inner states we have? 1, 2, 3, 4, 5, 6, 7, 8. Okay, and if we draw it, we have first to fall. Okay, so then here, and we have the 2, and finally this 2. And all these are p orbitals. This one is an s orbital. Okay, now make transition. So all the transitions within this inner state is forbidden. So every transition within this inner state is forbidden. This is because delta L cannot be 0. So we can only make transition from this group to this group. Okay, let's say first, if we choose this one, we have two transitions here, right? And you can think about that. Okay, if we choose this one, we also have 2. So that really depends on the number here times 2. Right? Because for each inner state, we can choose this one or choose this one to transit. So the total number will be 1, 2, 3, 4, 5, 6. 6 times 2 will be 12 lines. Okay? Will be 12 lines. So if you make the transition, you see the pattern, you will find 12 lines.
So are the spaces between the bottommost lines in the p orbitals and the space between the s orbitals, are those the same?
Well,
It's the same
no. That depends on there's the beta one, the term. The G times the Bohr magnetons times Mj times the magnetic strength. And the G factor actually will affect the energy gap. So usually for s orbitals, it would be wider than p orbitals. And this one is even smaller than this one. You can calculate and give the exact value, but here to show you, just to tell how many lines there, we can just draw them. But of course, this is not to scale. It's not to scale. Yeah, this energy gap is way bigger than the energy speed.
Right.
Way bigger.
was wondering if there were like degenerate energy levels.
Well, if they degenerate like this, they still have one transition, give you one wavelength.
Right.
Okay? So any questions about this? Okay, so different situations have different pattern to split. Okay, they're according to either L or ML or MJ. So those are just three situations. Okay. So that's so much for chapter 7. So chapter 8 talks about variational method or approximation method. Okay. And why we care about approximation method? So sort of the reason is you saw before. For example, is if we consider areas coupling, if we consider the magnetic interactions, it's impossible for us to solve Schrodinger equation analytically. And same thing for helium atoms as well. Okay, for helium atoms, our textbook says the inter-electronic repulsion terms makes this Schrodinger equation impossible to solve. Okay. In chapter 9, we will talk about how to set up the Schrodinger equation for many electron atoms. So here I just give to you. Okay. But I want want you to tell me which term is the so-called inter-electronic repulsion term. Or simply means which one is the troublemaker actually. What's the term for this? Kinetic energy. Kinetic energy for electron 2. So helium atom has 2 electrons. Number 1 electron, kinetic energy. Number 2 electron, kinetic energy. How about this? Potential energy. Or is potential energy due to attraction or due to repulsion? Attraction. You have nucleus charge here. Okay. Attraction. That's repulsion. Okay. You only talk about the E. Okay. So that's troublemaker. Because of this term, because of the presence of this term, we cannot solve the Schrodinger equation analytically. So instead, we need a approximation method to fight with those troublemakers. Okay. So this is the basic idea. And you will see actually besides this part, if we add any additional terms besides the kinetic energy and the attraction potential energy, we will not be able to solve the Schrodinger equation analytically. And instead we use approximation methods. And in this textbook, we only introduce you to the major two things, two approximation methods. One is the so-called variational method, and the second one is the perturbation theory. And for perturbation, we're not covering this year, so we only care about this one. So for variational method, the key idea is to use the trial wave functions to approach the exact energy. As we know, since we cannot explicitly solve the Schrodinger equation, so we cannot get the exact energy. But anyway, we can use the trial wave function, substitute into the Schrodinger equation, and we can solve the approximate energy. So let's say, for example, the exact average energy is defined as E naught, or means the ground state energy. I mean, the exact one, that means the true one, the real one, is evaluated by this expression. Okay, I use direct notation for you to understand that. So the top part here, the Hamiltonian operator is the exact Hamiltonian operator with the troublemaker inside, as I showed before. Okay. And then there are some wave functions. The psi. The psi wave function is the eigenfunction of the Hamiltonian operator. So it means the real wave function. Okay. And the bottom part is actually for normalization purpose. If your wave function is not normalized, I can do this one. So besides this, let's say, actually the top part, the numerator part is actually what we learned in chapter 4, to evaluate the average energy. So you still remember to evaluate the average observable A, we can use, let's say, for some space, right? So memorize this. So if you convert to direct notation, it's this. And we just make sure the wave function we used is normalized. If it's not normalized, we mentioned in chapter 4, please normalize it first and then do the evaluation. So over here, there's this one equation, well, 2-in-1. Normalization and the average value evaluation, the 2-in-1. So you combine them in this way, which just give you the average value. Okay. And anyway, this here, the expression we use the true eigenfunction of the Hamiltonian operator. That means the true wave function. And then we get the exact energy. But as I mentioned, because we have the troublemaker, this is not doable. Okay, we don't know. So instead, we need to use the trial image. We need to evaluate that with trial wave functions, also similarly as this one, with also the exact Hamiltonian operator, I mean with the troublemakers inside. But this time we use the trial function. So notice here I use different letters to represent. They're actually different. Okay, and again, this is for normalization purpose. But we'll talk about trial wave functions. So trial functions is some function you can try to plug in. In theory, any arbitrary functions, you can always just plug into the Schrodinger equation and try to solve it. But this is actually the trick here is how well you guess the trial function will give you different quality of approximation. So we'll talk about it. So here it just tells you show you the general picture. Let's say we have an image. And I mean the exact image level is this. So let's say we do the experiment. We experimentally determine that the exact image for that image level is E0. That's here. But if we want to use use quantum mechanics to evaluate, to actually calculate the exact image here, use variational method, we will end up with here. So always a little bit higher than the exact image. Okay, so that's actually the picture. So this E here is EP here, and E0 here is the exact image. So the trial image is always higher than the exact image, and we actually proved it in today's lecture. Okay. So in order to increase the quality, what I say in quality of the approximation, you can just lower your trial image further down and close to the exact image. Or even reach it. Once you reach it, it simply means your trial wave function, is the eigenfunction. But that's impossible. Okay. In theory, it's possible, but in fact, it's pretty hard for you to just catch that wave function. So you can always get something pretty close. So the closer your trial wave function is compared to the eigenfunction, the smaller this difference between your trial image and the exact image will be. Okay, so if this two closer, this two will also be closer. But always with your trial image be higher than the real image. Okay, that's a picture. Okay, so I want to talk about the trial functions. So guessing the trial function is actually the key steps for carrying out the variational method. Okay, the first step, and we'll talk about step here. The first step is to guess the wave function. So, well, it's not like by trying 1,000 of trial functions, doing that way. That's pretty time consuming. So you need to use some guidelines for you to guess the wave function. Okay, the first one should be scientifically valid wave functions. That means we should satisfy at least the boundary conditions, right? We wanted to guess the trial function for particle in the box. You want to choose a function which is 0 at two boundaries. If we choose a wave function that's not 0 at two boundaries, your approximation energy will be way higher than the exact one, because the quality is not as accurate. Okay. So you need to know something about your system in order to guess. Okay, at least, this is a pretty fundamental requirement. At least you should satisfy your boundary conditions. Okay. Second one is you should have some adjustable parameters for you to change your trial function. A typical way to do it is to use the Fourier combination of several basis wave functions. Do you feel this is kind of similar to you? When we talk about superposition, we talk about that. And we use this expression. Here again, we can use this expression as our trial wave function. So we say maybe F1, F2, F3, Fn, they are all sort of the functions, I guess, will be the eigenfunctions for the Hamiltonian operator. So I can just then combine them together. And next step is to minimize the trial energy. So first you need to evaluate your trial energy, and then you minimize it with respect to each factor, C here. So let's say you want to keep C2 to Cn as constant, fixed, and you only change C1. Once you change C1, you change your energy, your trial energy to be the smallest one. So here is actually the first order derivative for this one would be 0, and also the second order derivative must be positive. But it's not quite necessary here, because we know there's only one situation that you will reach a minimum energy, not a maximum energy. So this is somewhat just for the completion of the math, that's not quite necessary here. When you do the variation method, you only need to evaluate this part. Okay, so now once you find this equals 0, you get the C1, this is one of your coefficient, and you get this one, the optimize the C1. And you do the same trick, you change the C2, and you find the minimum trial energy, and you can optimize C2. So once you optimize all the Cn numbers, you actually, this is your trial wave functions. And by plugging into the Schrodinger equation, you can get the trial energy. Okay. Are there any questions about this? So if not, well, how can you improve the accuracy? I mean, the accuracy is the difference between your trial energy level with the exact energy level. Is by combining more trial functions. Okay, you can combine 1 more, 2 more, 3 more. But you also increase the amount of your calculation you need to do. But anyway, nowadays, most of those methods are carried out by the computer software. They have the programs to do this. So it can be finished within some time. Okay. And then, what I mean improve the accuracy is, actually this is your previous picture, you reach this level, this is your rest level, and now you can reach lower level, even lower. But keep in mind that always your trial energy should be higher, or the best situation is equal to the exact energy. But this equal is pretty hard to be reached. So you always end up with something higher than that one. But just depends on how high, compared to the exact one. Okay. The closer, the better. Okay. Any questions? Okay, well, I think that's all. Thank you.